Here in this particular question, general purpose op amp cannot be used for the application. There are different kinds of applications of general purpose op amp have been given to us. The first one is integrator, second one is audio power amplifier, third one is differentiation, and the fourth one is summing amplifier. So here we can see that this particular question, we have studied the applications of an op amp in our curriculum syllabus, and we have studied that op amp can be used as an integrated, op amp can be used as a differentiator, op amp can also be used for as a summing amplifier, scaling amplifier, and also we have seen it for averaging amplifier. So now among those applications which we have studied here in our curriculum, and more than apart from that one, we have seen op amp can be used for log applications, anti-log applications, for doing some linear equations, solving some linear equations, and also can be used for solving some differential equations. But here in this particular question, out of the four options which are given to us, integrator is we have studied as an application, and again we have studied differentiation as an application, and also summing amplifier as an application. The odd option over here is the audio power amplifier. It means what? Op amp cannot be used as an audio power amplifier. Audio power amplifier is what? Audio power amplifier is a special purpose op amp, and it is used only for some specific applications. But here in our question it is given that you tell which of these options where op amp is used for purpose application, for a general purpose application. This one we have to look at this one, where audio power amplifier means what? It's a special purpose one. It's nothing else but you might have seen power amplifiers. Power amplifiers of different huge setups will be there which will be connected to the big speakers. That setup where the sound which goes through the mic into the amplifier, and that amplifier will be amplifying, and the output of the amplifier will be given to the huge speakers. So that setup is called as a power amplifier. So now here the odd one, power amplifier is not a general purpose op amp. It is a it's a special purpose op amp. So this is your correct answer. Option B is the correct answer. Second one, the special designed comparators are compatible with different kinds of options: RTL, that is a register transfer logic, MOS logic, TTL, and all of the mentioned. So we are talking now here about the comparators. So now here option is one, the special designed comparators are compatible with what? In RTL we'll be doing some comparisons, register transfer logic. In MOS logic also we'll be using the comparators. TTL logic, transistor logic. TTL means transistor logic. In all these applications, all these different kinds of logics, we are using the comparators. So it's a compatible one. So your answer is D. D is your correct answer, because your comparators are compatible with all the different kinds of logic. First one is RTL, that's a register transfer logic. Second, MOS logic. Third one, TTL. TTL means transistor logic. Let us see now the explanation. The special designed comparator outperforms the op amp type. They are optimized for a most desirable promoters like speed and accuracy. So their output is compatible with RTL, DTL, and again TTL and MOS logic. So in this all different kinds of logics, all these logics are very much familiar with the VLSI, where you will be looking for the high speed and accuracy. So the comparators are compatible with all these logics. So answer is D, all of the mentioned above. Then next one, the response time. The response time of comparators is defined as, now let us see, it is an important formula for this one, where you will be studying about this one. The options are time interval between input and output crossing upper threshold voltage, time interval between input and output function, time interval between input and output crossing threshold logic, and again time interval between input and output crossing lower threshold logic. Here out of this one, if you see, all looks like alike, all look like the same. But here we have studied that the response time of a comparator is nothing else but it is a time interval. It's a time difference or the time period between input and output crossing threshold logic. So let us see now the explanation here. The response time of a comparator is a interval between the application of input step function and the output time output crosses the logic threshold voltage. You have studied about different kinds of threshold voltages. First one is a upper threshold voltage and second one is a lower threshold voltage, and the time period between this upper threshold voltage and lower threshold voltage we have studied as a noise margin. So it is a we have studied about the hysteresis. The hysteresis voltage we have studied. That hysteresis voltage is nothing else but it's the time period between the upper threshold and the lower threshold voltage. We are covering now here in this particular question. We are covering the two questions. First one is regarding the response time of a comparator. Response time of comparator means what? It is a time interval between input and output crossing threshold logic. Means here whenever you give some step function, it's a time between the application triggering that step function and the time output which crosses the logic threshold voltage. The time whenever the output crosses the logic threshold voltage and the input which you applied, that is the time response time of a comparator. Then what about the hysteresis voltage? Hysteresis voltage is nothing else but it's a time period between the upper threshold voltage and the lower threshold voltage. Hysteresis voltage. That hysteresis voltage only I have given in class regarding the explanation of noise margin. Okay, so hysteresis voltage is a time response or the time period between the upper threshold voltage and the lower threshold voltage is hysteresis voltage, and don't get confused between hysteresis voltage and the response time of a comparator. In the response time, it is a time period between that you apply the input voltage and there is some output is obtained. That output has to cross the threshold voltage. So whenever the output crosses the threshold voltage, from that point to application of the input, this both the time period we call it as a response time of a comparator. Then what is the hysteresis voltage? It is a time period between the upper threshold voltage and the lower threshold voltage. So now we have covered here two questions. As per this particular question, your answer is C. So third one is your correct option. Third one is your correct option. Now next one. The voltage level at which comparator saturated by a differential input equal to greater than a specified voltage is called. The voltage level at which your comparator is saturated. Your comparator is completely saturated. Means what? Your comparator enters into the saturation region by a differential input equal to greater than a specific voltage. You are supposed to tell at what voltage your comparator is entering into the saturation. So now let us see first the explanation and we'll come back to the options. Explanation. The negative output level or the output low voltage is the negative DC voltage drop with comparator saturated by differential input equal to or greater than your specified voltage. So your comparator is going to get saturated at a negative output level, not at the positive output level. Your comparator will be always saturated at the negative output level. That is a option C is the correct one among this four. Zero output level or positive output level or all of the above. Among this third one, C, negative output level is the correct one. Fifth one, which of the following comparators can operate from plus or minus 15 to down to plus 5 volts supply in an op-amp? Which of the following can be operated from plus or minus 15, which can come down from plus or minus 15 to plus 5? Means even at the plus 5 voltage, your comparator will be, this particular kind of comparator will be working. It will not, it will not degrade the output. It will be working and giving this almost the same kind of results. So that for that one, the example here among the options which is given is 741, 311 and 351 and all of the above. Among this one, 311 op-amp or the 311 comparator precision, it is actually a precision comparator. 311 is a precision comparator. It is designed for low level signal detection and high level output driving capability. Means what does this comparator do? It will compare or it will identify low level signals, and also it will drive means what? It can easily give out the output, and that output can be given as an input to the next level of the circuits. That is a driving capability. Output driving capability means what? If you are having one circuit, that circuit output has to easily signal out some output data, and that output data should become as an input to the next level circuits. That is called as a driving capability. In digital logic, we have studied about fan in and fan out. Fan in is nothing else but how many inputs we are triggering to the logics, and fan out is nothing else but to how many circuits or how many gates one particular gate output is driving. That's the fan out. In the same way here, this particular 311 precision comparator has got a capability of driving it is having a large capability of driving the outputs. So it can operate from plus 15 volts op amp supply down to logic plus 5 used for the IC logic, used for an integrated circuit logic. So your options B is the correct one here. The option B, 311 comparator is used where it can work at plus or minus 15, which is op amps operating supply, to it can come down to plus 5 volts. Next one. Find the comparator that has slow response time. Just now we have studied about the response time. What is response time? Response time is a time interval between the time we apply the input voltage to the time where your output will be crossing some threshold voltage. It has to cross some threshold voltage. So the time interval or the time period between the application of the input to the output crossing the threshold voltage is called as a response time. We know that one. So now you are supposed to out of this one, which is having the slow response rate. Out of this one, the first one, 1414 comparator, LM1414 comparator will be having the slow response time. So it has a slow response time typically of 30 nanoseconds, where this one AF, micro AF 311 and ICL 8 has got response time of 200 nanoseconds and 50 nanoseconds. So out of this one, which is the slowest one? The slowest one is the first one. Option A is the correct one. Option A is the correct one. Next one. Why ICL 8001 op amp comparator is preferred for most of the applications. Now let us see some this one. Here in this one, why it is preferred? Because this ICL 8001 op amp is a low power consumption. We all know that nowadays every circuit or IC has to be worked in a low power operation. It has to have a low power consumption. It has to operate in a low power mode. Why? Because if it is operating in a low power mode, definitely because the device size is shrinking, because the transistor size is coming down day by day. Means I'm talking about the size of each and every transistor. If a transistor size is shrinked means it is reduced, then definitely we can accommodate more number of transistors on a single IC, and we can get more applications out of it. We can use the same IC size for many different applications. I'll give you one example over here. Earlier we used to have for some phones like Nokia phones, which were very hard and very small to handle, but hardly it was very heavy also. We used to hardly perform some operations in that one, like it would do only calling, and it would do some small calculations, and it would have one small games like snake game. So it was only hardly it used to do some small operations. But nowadays what has happened? Because of the shrinking of the device, because of the shrinking or reducing of that size of a transistor, now we are able to accommodate more number of transistors on that integrated circuit. If you are accommodating more number of transistors, means what? You are building more number of different circuits over there. Because of that, constructing of different circuits. Circuits means what? It can be any kind of circuit now. It can be a circuit which is used for your image processing. Because of that one, we are having very high defined cameras in our mobile phones. It can be used for high speed operations. Because of that high speed operations, nowadays in every mobile phone we are having a very high speed gaming opportunities are there, where you can play and use your mobile phone for a high speed games. And it is having a very good camera capability. It's having very good touch screen capability, and nowadays even the Bluetooth versions are changing, means very fast data transfer is taking place. So all these are the different kinds of circuits. So all, and again one more thing, earlier when you talk with the older generation phones, the phone used to get heated up very fastly. But nowadays what is happening, because the technology is improving day by day, electronic technology is improving day by day, we are having a cooling system in the mobile phone itself. Even if you game for a longer time, it is not going to become power dissipation is not more, heat is not produced more. So that's why in order to have a low power consumptions, we are using this kind of comparators. These comparators are mostly used for the low power consumption, where it can consume only some amount of power. So what is the power consumption of this ICL 8001? It's hardly 30 milliwatt. 30 milliwatt of power it can consume by doing some comparisons at a lower power operations. So among this one, your option A is the correct one, where ICL 800 amp comparator is used for low power operations. Next one, which op amp is preferred for applications like high speed A to D converter and zero crossing detector? We have studied this one already in the class. Which these applications we have studied, A to D converter and zero crossing detectors. So among this one, 670, among the four which you are talking here, among the four, 670 is a high speed differential voltage comparator with a TTL logic, with a transistor logic. It has been defined or designed, and it has got a typical response time of 60 nanoseconds and operates from plus or minus 4.5 to plus or minus 6.5 voltage. See now the response time of this one. What, right from the time you give some input to this op amp or a comparator, and the time it crosses the threshold voltage, that is the nanoseconds. It's in the nanoseconds. Means what? It is used for a high speed operations. It is used for a high speed operations. Here itself we can tell that high speed they have given for operations. So among this one here, the first option here, option number D is the correct one, which is used for the high speed operation. 670 comparator is used for high speed operations. Now, which circuit can be used as a full wave rectifier? Full wave rectifier, we have studied about different types of rectifiers in our EDC, electronic device circuits, different kinds of subjects. We have studied about this half wave rectifier, full wave rectifiers, and bridge rectifiers, and different kinds of rectifiers we have studied. Here, which circuit can be used as a full wave rectifier? Among these options which are given to us, absolute valve output circuit is used for this one, absolute value output circuit. See here, it's actually U is missing over here. It's an absolute value circuit, output circuit. Absolute value circuit is used for full wave rectifier. Why? Because the absolute value circuit produces output signal that swings only that will swing only positive only. It's a full wave rectifier. See here now, regardless of the polarity of your input signal. Means this particular circuit which is mentioned over here, it will be swinging only positively regardless of what kind of signal you are given. Because of this nature of its output waveform, the circuit can be used as a full wave rectifier. The concepts of full wave rectifier, half rectifier, easily you can understand what is the meaning of this particular explanation. This circuit, absolute value output circuit, is used only for where your output of this one circuit will be used for swinging of only positive signals. So that is about the full wave rectifier. So option A is the correct one. Then the next one. Here is a numerical depending upon one circuit is given to us. For the circuit shown below, find the output voltage. We are supposed to find out V out. We are supposed to find out this particular, excuse me, where is my cursor? Yeah, it's over here. You are supposed to find out V out here. We found out their options are being given, and they have given that what is the value of V out. Let us see now here. See now, the output at the terminal. What is the output at the terminal? The output at the terminal V1. Where is my V1? The output at the terminal V1 is what? You can easily apply the network theory concepts, and you can find out what is the output over here. The output at the terminal V1 is equal to Vp minus VD1 VD1 divided by 2. When you apply this concept over here, it is a Vp is what? Vp is equal to 12 volts. And what is this one? This VD1 is the voltage which is of 0.7 for this one. What is that? We call it as a cut-in voltage or threshold voltage divided by 2. You get ultimately V in value you get. V in value, the voltage across this one you get here. You get the value of V in over here. That V in is equal to 5.65 volts, where VD in is a voltage drop across the diode. That's what I told you here. It is a minimum voltage required for that turning on of that one. That is a 0.7 of the diode. Similarly, the voltage at the negative terminal. Is V2 is equal to, we can easily find out this formula by using the same network theory concept. It is equal to what? Again, you are having the two voltage source. That is V out minus this particular voltage drop. So V out minus this voltage drop divided by 2. So ultimately, we are going to have the power divisions over here. That's why it's divided by 2. You get V out minus 0.7 divided by 2. So you are going to get here, since VID is almost equal to 0 over here, V1 is equal to V2. V1 is going to V2. How come the V1 is going to be V2? It's application of concept called what is that concept we have studied here? The concept we have used over here, that concept is nothing else but it is regarding the short short circuit between these two voltages. Between these two, whatever the voltage is present at V1, that is also equal to voltage at V2 will be the concept of this one. So that particular concept we have used here. That concept, when you apply this concept here, V1 is equal to V2. You're going to get this formula. V1 is equal to V2, and V out is equal to what? Ultimately, V out is equal to 5.65 into 2 plus 0.7. That is equal to 12 volts. You do some mathematics over here, you're going to get this, but 1. So ultimately, your answer is equal to 12. That is equal to B. So output voltage we have calculated, that is 12 volts. Can anyone tell me how V1 is equal to V2? How V1 is equal to V2? Please talk to me.
Virtual ground concept.
Good. It's a virtual ground concept. Because of the virtual ground concept or virtual short concept. So here V1 equal to V2 because of the virtual ground concept, call it as a virtual concept, or else we call it as a virtual short concept. Because of the virtual short concept, V1 is equal to V, and apply the formula here. When you apply the formula, both are being equated. If you equate these two, ultimately you are going to get the answer. You are going to get the answer. Finally, that answer is equal to 12 volts. Okay, now we have completed 10 sets of numericals upon this particular concepts of op-amp, which are being used for used for constructing of the comparators. Almost all these 10 questions were regarding the op-amp used for constructing the comparators.